Hello everyone, I'm Xiaoqi. In previous episodes, we shared how we used AI to develop a ground station and how AI can take over drone control. Our company has now fully entered the era of AI-assisted drone development. Based on this trend, we launched the AI Creation Project, which uses AI to build drones and compress development cycles. Some tasks used to take 6 months, a year, or even 1 to 2 years. With AI programming tools, we can shorten that work to about 2 months. In some cases, it can be shortened to about 3 months, which greatly improves our development efficiency. In today's video, we want to go deeper and share a classic case, walking through the complete workflow, using AI to port and reproduce the fuel algorithm. Okay, let's get started. Today, I'll share how to port and optimize the fuel algorithm. We start with simulation, verify the core planning logic and mapping results, and then deploy it onto a drone equipped with our FlyCore integrated control system, enabling autonomous garage exploration and mapping in a real-world environment. Fuel is a classic exploration and mapping algorithm. Its original architecture is based on ROS1. Since most of our later drone platforms use ROS2, the first step is to port Fuel to ROS2, update the communication framework, and make it compatible with drone software. Then we connect it with our ProSim simulation system. After validating it in simulation and confirming stable planning performance, we migrate it to the FlyCore hardware platform and implement it on a physical drone. To make future optimization and development easier for other developers, we have also open-sourced the AI written code and algorithm. The complete project is available on Git, where you can find the source code and related files. You can see the name of FlyCore Fuel Recreate. You can download the reproduction project if you need. Throughout this process, we barely wrote any code manually. We mainly provided reference interfaces, several markdown files, and clear development instructions for the AI to follow. We also provided sample code for the AI to study and use during integration. To carry out this AI development effectively, we need to prepare the tools and development environment. First, the AI tool I use is Codex. We make the environment capable of programming. Second, we prepare the ProSim simulator to testing algorithm verification and preparing the later deployment. Third, we locate the Fuel project repository so we can build our project. Fourth, we prepare the project files. For the reproduction workflow, the first step is to prepare architecture documents and interface documents. I have emphasized this repeatedly because this directly determines whether the AI can generate usable code. These architecture and interface materials are essentially markdown files that we feed to the AI at the beginning. You can see them directly in our project. They are not just simple notes, but structured instructions that define the project architecture, module relationships, communication interfaces, and implementation constraints. These MD files guide the AI, telling it how to work, what to build, and which rules. This is a critical step. At the start, we spent about 2 days preparing and thinking through these files. The quality of that preparation can determine whether the project succeeds. This matters a lot. The second step is letting the AI learn the project and help us build it. Once the files were ready, we told the AI to read them thoroughly and build the project locally. During this process, it first reads our MD files, understands the architecture logic, and identifies the key development tasks. Second, it creates the project structure, sets up the Git repository, configures the basic directory layout, and prepares the initial development framework. Third, it pulls the fuel source code repository, reads the full fuel code base, and reviews its README files to understand the original algorithm logic and dependencies. You may also need to interact with it during this process and repeatedly emphasize that it must strictly follow the MD files we provided instead of making assumptions or changing the architecture on its own. The third step is process supervision. In total, our conversations with the AI took more than a week. During that time, it ported the original fuel algorithm to ROS2, adjusted the related interfaces, fixed compatibility issues, and gradually connected the algorithm with our simulation and hardware deployment workflow. It then implemented a simple gazebo simulation and later moved into a more complex ProSim simulation with LiDAR added, which allowed us to test the exploration logic under more realistic conditions. During this stage, I tried 2 approaches. The first approach was to review its reasoning, solution path, and methods after every step it completed. I checked whether they deviated from our original architecture assumptions. The AI often tends to get trapped in code-level details or parameter tweaks, while losing sight of the overall system design and development direction. So I repeatedly reminded it to optimize according to the original logic, instead of inventing its own algorithms. That helped bring it back on track. This is the supervised development workflow. By the middle and later stages, its code architecture had become much more mature. Its implementation approach was also relatively mature, and the architecture itself had become stable enough for continuous testing. At that point, I could switch it into an unsupervised mode. I told it that I was no longer at the computer and that it needed to modify the code, run the program by itself, observe the results, and continue fixing problems based on the feedback. It would monitor each ROS node for about 2 minutes and check whether the messages met our requirements. If not, it would stop, modify the code, and run the test again. This created a self-supervised, self-running workflow where the AI could continuously debug, verify, and improve the system on its own. It works best when the architecture is already finalized and the results are reasonably good. This method is especially suitable for the middle and later stages of development. The AI can handle repeated testing more efficiently and reduce manual debugging work. The fourth step is running the system in our ProSim simulation. ProSim uses the UE5 engine, which makes the environment more realistic and more convenient. Step 5 is physical drone testing once the simulation results are satisfactory. Now let's look at the reproduction results. This is a garage environment, and this is the point cloud data in RVAs. At the beginning, the point cloud is not very dense because the drone has only observed a small part of the environment. As the drone flies and maps, the point cloud gradually becomes denser and the structure of the garage becomes clearer. This matches our setup: mapping while flying, exploring while flying, and building a map of the entire environment. We spent a little over a week and the algorithm simulation is almost tuned. Next, we may deploy it to the physical drone. This follows our strict development process. If we see issues in simulation, we do not move to the real drone. We solve the problems and proceed to real-world testing. Okay, that is our overall development workflow and process. Let's summarize. First, prepare architecture level and global materials, including a large number of markdown files. Second, let AI learn the project and help build it. Third, at the beginning, we used a supervised development mode, so we could keep the AI's output under close review. In the middle and later stages, we switched to a mode where the AI was allowed to optimize autonomously, although this consumes more tokens. Fourth, we performed extensive testing and flight validation in simulation to ensure there were no issues on the real drone. Fifth, we can then begin physical drone deployment. Those are the 5 steps. One small detail: remote login is very useful because it lets you work from any environment. Even before going to sleep and from almost any environment, you can still direct the AI to keep working. By that point, you already have a solid understanding of the overall architecture and can control the quality of its output. In the past, porting the fuel algorithm would have taken at least 3 to 6 months to complete the whole process from simulation to real drone reproduction. Also, this version is not identical to the original source code. It includes substantial ROS 2 porting work, as well as optimization and adjustment for the PX4 controller. We also had to adapt the system architecture, communication interfaces, and deployment logic. This is not simply a case of downloading fuel and using it directly. The original fuel algorithm does not provide an interface for PX4. To migrate it to ROS 2 and integrate it with PX4, there is still a significant amount of work involved. This includes message conversion, control command logic, trajectory output, and compatibility with the flight control stack. Later, we will continue testing the code, including simulation validation, stability optimization, and real drone tests. We will also test its interfaces to improve stability and robustness, so it can be truly applied in real industrial sites and industrial environments. We have also uploaded and opened the code to everyone, making it easier for developers to reproduce, verify, and continue improving the system. We hope that based on this work, you can continue optimizing and iterating with our FlyCore platform or with your own drone, and adapt it to more real-world application scenarios, so we can improve drone development efficiency. Okay, we will bring more updates and sharing around the AI creation project. Let's embrace this great era together. I hope this video series gives you useful insights and practical value and helps you better understand how AI can be combined with drone algorithm development. If you have any questions, feel free to like, share, and leave a comment. We will answer everything we can. Okay, thank you. See you in the next episode.